Namaste and hello everyone. Welcome to the Civil Academy. We have seen in the previous class regarding the evolution of cement. If you have not seen it yet, please click on the I button as some of this content over here are related to the previous video. Now, in that we have also learned how the properties of Portland cement resemble the natural stone which is quarried from Portland, that is a UK. So in today's class, we will see the following content, that is the grades of cement, the chemical composition of all the grades of cement, the physical composition of all the grades of cement, the oxide composition of cement, and most importantly, the Bogue's compound. So firstly, let us learn about the raw materials of Portland cement. Portland cement is prepared by mixing mainly two types of material in definite proportion, and they are calcareous and argillaceous material. Now, the materials which provide us with lime is generally called as calcareous material. For example, limestone, in which we can find about 65 to 80% of CaCO3, that is calcium carbonate. Then chalk, calcite, etc. The word argil means clay, that is clay is predominating here. Now the material which provide us with silica, alumina, iron oxide is generally called as argillaceous material. For example, clay, marl, shale, etc. In addition to these main raw materials, we also add gypsum, whose chemical formula is CaSO4.2H2O, and powdered materials. Now, if we summarize all the raw materials, we can say it to be lime, alumina, silica, iron oxide, and gypsum. And all these have very specific roles to play in the cement. So these raw materials should be mixed in definite proportion so that the clinker formed must have proper constituent. Now, before learning about the composition of cement, let's learn the grade of the OPC or ordinary Portland cement. There are namely three grades of cement, that is 33, 43 and 53 as mentioned over here. Here I have mentioned regarding the code of all the three grades of cement. If you go through this code books, you will find all the details regarding the specific grade of cement, like in IS 269 1989, which was first published in the year 1951, and it was revised in the year again in 1958, then in 1967, then in 1976, and finally in the year 1989 it was published. OPC 33 grade must meet the chemical specification as well as the physical specification which is listed in this code book. Now, these chemical and physical specifications which are mentioned is tested using the procedures outlined in IS 4032. Similarly, for OPC 43 grade, the IS code was published in the year 1976 and it was revised in the year 1989. For OPC 53 grade, the IS code was published in the year 1987. If I talk about the properties of cement, it can be divided into chemical and physical properties. Here we can see a direct comparison of chemical requirements for the OPC 33, 43 and 53 grade of cement as given in their respective IS codes. We have already discussed earlier about the very main constituents of cement, that is lime, silica, alumina and iron oxide. Now, there is an approximate limit fixed for the chemical composition of cement. As you can see all the values over here, this is from the IS code books. Any change in this limit may lead to the change in the behavior of the cement. For example, suppose we increase the lime content, it makes it difficult to combine completely with other compounds. This also may lead to the increase in free lime, which finally result in an unsound cement, and that is very much practically not acceptable. Here we can see a comparison of all the physical requirements of OPC 33, 43 and 53 grade of cement as listed in their respective IS codes. Like the first characteristics of cement is the fineness of cement. The fineness of cement generally tells us about the particle size or the size of the particles of cement. In the final step of manufacturing process, the clinker is ground to the requisite fineness for excellent cement. The fineness of cement is very crucial because the rate of hydration of cement and the particle size are very much correlated. Like, the finer the cement, the greater is the surface area and the faster is the rate of hydration. Then the second characteristics of cement is called as the soundness of cement. The ability of the cement to resist shrinking after hardening is referred to as soundness. That means cement should not undergo any kind of volume change. The good quality cement does not change in volume after setting. So the excess or the change in the volume is caused generally due to the excess amount of free lime and magnesia present in the cement. Then let's see the third characteristic, that is the setting time of cement. So all of us know that when we add water to the cement, it hardens. So this setting time depends mainly or basically on three factors, that is the fineness of cement, the water cement ratio and the admixture added to the cement. So normally the initial setting time, it should not be too low and the final setting time, it should not be too high. So for that we have to calculate two setting time of cement, that is initial setting time and final setting time. So initial setting time is the time when the paste just begins to stiff. That is, normally it takes about 30 to 45 minutes. The final setting time is when the cement hardens or can sustain load, that is around 10 hours after application of water to the cement. And the last characteristic is the compressive strength of cement. The compressive strength is the most common strength test of the cement. Here what we do is, we have to prepare cube samples, then cure the samples and test it using the compression testing machine. If we can take this, or we can see this in the table, the values mentioned for OPC 33 grade of cement after 3 days of curing is found out to be 16 MPa. This is 3 days of curing. After 7 days of curing, it is found to be 22 MPa. After 28 days of curing, it is found to be minimum of 33 MPa and maximum of 48 MPa. Now, this is why it is called as OPC 33 grade of cement. This is the reason why it is called. Similarly, for OPC 43 grade, after 3 days, we get it to be 23 MPa. After 7 days, we get it to be 33 MPa. After 28 days, it is 43 MPa and maximum of 58 MPa. And that is why this is called as OPC 43 grade. And this goes same with the OPC 53 grade. After 3 days, we get a strength of 27 MPa. And after 7 days, it is 37 MPa. After 28 days, it is 53 MPa. Now here, I would like to draw your attention to one small practical thing which you might have heard. That is, whenever we construct a new house or anything with concrete, it is advisable to pour water to that concrete for 1 month. So instead of 28 days, we say it to be 1 month. So now you can understand why it is advisable to do that for 1 month. Before learning the oxide composition, let's see the abbreviation which is used in the cement chemistry. Like here, the C stands for CaO and not carbon. This S stands for SiO2, A stands for Al2O3 and so on. The alkalis does not have any abbreviation, so I have just mentioned it to be as alkalis. So all the percentages you can find it over in this chart with the names of the compounds. So let's see the first one, that is lime. As you can see, the average of lime present, this is the chief constituent which is present in the cement. This mainly impact on the strength as well as soundness of cement. Now, if it is present in less amount, then it reduces the setting time as well as strength. Then coming to the next is silica. Silica, it provides strength to the cement, and if it is present in excess, it reduces the setting time of cement. The next is alumina. Now, this alumina is responsible for the quick setting of cement. If it is present in excess, it reduces the strength of the cement. Then next one is iron oxide. This helps in fusion of different materials. Now, apart from this, it also imparts grey color to the cement. Next is MgO. It provides hardness and also color to the cement. Now, if it is present in excess quantity, it causes cracks in the mortar and produces an unsound cement. Then SO3, it imparts soundness to the cement. Now, in addition to this, a small amount of alkalis like Na2O, K2O, TiO2, P2O5 are present as residues in cement. Now, if these alkalis are present in excess, it causes efflorescence. And this results in cracking of concrete. So, if we summarize this entire table, I can say this lime and silica is generally responsible for the strength of the cement. Alumina, if I say it, is always in a hurry position, and as soon as it sees water, wants to react, and due to this, the strength is reduced. हिंदी में कहावत है ना, जल्दी का काम शैतान का होता है. So this is similarly to that. Now, lime, what it does, it increases the setting time, and alumina, it decreases the setting time. So if you can see, this both are opposite to each other. And iron oxide, as I have said, it provides a greenish grey color to the cement. Now, if you want to remember, there is a very small trick you can say. Not a great one, but still you can remember this. Lalit and Sarah aims at apple. Just take the first letters, that is L, S, and take this A, I, M, M, S and A. So this represents your lime, silica, alumina, iron oxide, magnesia, sulfur trioxide and alkalis. Before learning Bogue's compound, let's once again remember the word clinker. This is a picture of a clinker, of clinkers you can say. This we have already seen in the previous video, which will be linked in the description box below. Moving on, we have already seen the oxide composition of cement in the previous slide. So, the oxides that fuse with one another creates a variety of complex byproduct, including this cement clinker. So, the substances which is produced during burning, it has the abilities to set and harden in the presence of water. That is, if you add water to the cement, it reacts and form a very complex compound which is known as Bogue's compound. Now, these substances were discovered by a person named R.H. Bogue or Robert Herman Bogue, and as a tribute to him, they are known as Bogue's compound. You can see the picture. Moving on, Le Chatelier identified 4 distinct crystal types by microscopic examination of thin cement clinker sections, and these crystal types were eventually termed as alite, belite, salite and pelite. And these were named by Alfred Ellis. Now, if you can see this microscopic view and mark this one by one in the picture, then this represents, the first one represents the belite, that is C2S, is also called as belite. This is C3S, which is called as alite. This is C3A, which is also called as salite. And the last one is C4AF, which is called as belite. This belite is somehow you can say its color is white. Alite is also white in color. Salite is white or grey in color. And this pelite, it looks like black in color. So you can see over here all the Bogue's compound which is mentioned in a tabulated form, and you can see the percentages also in this chart with the compounds. So the compound name you can see again is tricalcium silicate. This alite which I have told in the earlier slide is also by Bogue, it was named as tricalcium silicate. And the chemical formula for this is 3CAO.SiO2. The abbreviation is C3S. And you can see the average percentage over here. It ranges from 25 to 50, but on an average, we take it to be 40%. Similarly, the second one is dicalcium silicate, which is also called as belite. This is the chemical formula. This is the abbreviation, and its percentage also is in between 25 to 40, and we take it to be 32% on an average. You can see this in the chart itself. It's very clear. Similarly, for tricalcium aluminate and tetracalcium aluminoferrite, the percentages are 10.5% and 9% respectively. Now, let's discuss this. So, as we have seen in the previous slide, the Bogue's compound, the first one is tricalcium silicate. We have already seen the percentage. The average percentage of C3S is taken to be 40%. So this is regarded as the best cement ingredients, or we can say the most important clinker constituent that governs the strength of the cement, and it is provided in it provides the early strength and is also responsible for 7-day strength of the cement. Now it makes the grinding of the clinker very simple or very easy, and the resistance to freezing and thawing is also increased with the presence of this C3S. The heat of hydration generated is high, and that's why it lowers the ultimate strength, and the heat of hydration is about 500. Then coming to the next is C2S, dicalcium silicate. So here hardening occurs in later stage, that is it takes around 7 days to 1 year, because it takes time to hydrate, which is important to note. Then it enables the clinker, or you can say it is very hard to grind. The resistance to freezing and thawing decreases over here, and it imparts chemical resistance. The low heat of this heat of hydration is very low. It is generated very low here, and the heat of hydration is, you can see also, it is 260 only. Then the third one is tricalcium aluminate, or C3A. This is the first compound which is formed or which is reacted with water. I have already said in the oxide composition that alumina is the, you can say it is always in a hurry mode. Okay, so that is why this is the very first compound which is formed, and this is formed within 24 hours of mixing water with the cement. So this decreases the setting time and increases the shrinkage and cracking of the cement. So if it is present in more quantity, this reduces the setting time, it reduces the resistance to sulfate, it reduces the ultimate strength and also the heat of hydration. And generally its heat of hydration is about 865. And the last one is tetracalcium aluminoferrite, that is C4AF. So this is, you can say, this value of cementing is very least, or its cementing value is very least than any other. So this is responsible for the flash set of cement along with C3A. That means this is also produced within 24 hours of mixing water with the cement. If we increase its content, it reduces the compressive strength and it also imparts chemical resistance. Its heat of hydration is 260. Now, if we, on the basis of formation of this compound, if we say, then C3A and C4AF is formed fast. It is formed faster than both the two, that is C3S, and then at last C2S is formed. Now, if we summarize it, then the best cementing property is provided by this C3S. So, as we have already known that cement has a property of binding or bonding, and it's mainly due to this C3S and C2S. So, if we differentiate this C3S and C2S, then in C3S, clinker is easy to grind, okay, whereas in C2S, clinker is hard to grind. In C3S, high heat of hydration, whereas in C2S, low heat of hydration. In C3S, the high heat of hydration is 500, whereas in C2S, the heat of hydration is only 260. The solubility of cement increases with water in C3S, whereas the solubility of cement decreases with water in C2S. What a great line said by an American football player, is also a coach, that confidence is the invisible cement that binds a team together. On that note, see you all in the next class. Keep learning. Thank you, everyone.